Okay, so let's continue with our discussion of linear programming problems and see how we're going to go about solving them. The problem that we talked about last time with furniture and limited storage was expressed in terms of constraint equations and an optimization function. So here are the constraint equations that we had. This was the limit by the amount of money, this was limit by the amount of storage, and this expresses the fact that number of tables and number of chairs has to be positive. Now I mentioned previously that these look like the equations of lines. So let's go ahead and draw the lines corresponding to all these expressions. Now if you have a less than or equal to, that's not a line, that's a region or a half plane. But let's go ahead and plot the lines 5x plus y equals 100, x plus y equals 60, x equals 0, y equals 0. If we do this, x equals 0 of course is here, y equals 0 is here, and then we have x plus y equals 60. Well, on the scale that we have here, x plus y equals 60 is this line. An easy way to draw lines when they're expressed this way is you set each variable equal to 0 one by one and find out what the other variable is. For example, if y is 0, then x is 60. Remember, I'm plotting the equality now. We'll get to the inequality later. So when y equals 0, x equals 60. When x equals 0, y equals 60. So that means that the x-intercept is 60, 0, and the y-intercept is 0, 60. On the other hand, if I look at this equation here, when x equals 0, y equals 100, and when y equals 0, x equals 20. So the x-intercept is 20, 0, and the y-intercept is 0, 100. Okay, so that's going to be this line here. We can see x-intercept 20, 0, y-intercept 0, 100. So here are the lines that correspond to those constraints. Now what's this blue here doing? Well, remember, now we get to the inequality part. This one says 5x plus y is less than or equal to 100. Alright, now we know that this is going to be one side or another of the line that we drew. When you have an inequality, that means that you're on one side, you can't cross over the line. Now the question is it the side up here above the line, or is it the side down here below the line? And the easy way to determine that is figure out whether or not 0 is in the region. When I say 0, I mean x equals 0 and y equals 0. So in fact, x equals 0, y equals 0 is in this region because it satisfies this inequality. So since it's in the region, that means this point 0, 0 must be in the region in question, but 0, 0 is below the line. Therefore, that region corresponds to, we could shade this area here, all this part here. Similarly, this other constraint, x plus y less than or equal to 60, 0, 0 is in this region because it satisfies the constraint. So that's everything below this line here. Finally, we have x greater than 0, y greater than or equal to 0. So x greater than 0 means everything above the x-axis. Y greater than or equal to 0 means everything to the right of the y-axis, so we need to restrict ourselves to the first quadrant. Now if you take the intersection of all the shaded regions that we've indicated, that is this blue region. So in this blue region, all four inequalities are satisfied. So this is called the feasible region because feasible meaning possible. These are the set of all possible strategies x and y that satisfy all the constraints. And any point outside the feasible region is called infeasible. All right, so we have this polygonal shape that determines the feasible region. Okay, so now I said that all of the points in this blue area are feasible. Any one is a possibility. An infinite number of possibilities, how do we find the best one? Well, it turns out that there are some guidelines we can use, and we'll see why these guidelines work shortly. So the first guideline we call Theorem 1. So let R be the feasible region, and this feasible region is called a convex polygon. I'll explain that in a minute. So the feasible region for a linear programming problem, and let z equal ax plus by be the objective function. Remember, our objective function does have this form. Now, when z has an optimal value, maximum or minimum, the variables x and y are subject where the variables x and y are subject to the constraints described by linear inequalities. This optimal value must occur at a corner point or vertex of the feasible region. All right, so let's unpack this a little bit. Here we have a region here, which I said it looks like a polygon, and he says it's a convex region. So let me explain what convex and non-convex are. All right, so here's an example of convex. And here's an example of non-convex. Okay. Now you can see visibly a difference between these two. One way you can characterize this is if you look at all of the exterior angles. All of the exterior angles are all greater than 180 degrees. So that's one way of characterizing convex. So you have these exterior angles greater than 180 degrees. Now if you look at the exterior angles here, some of them are greater than 180 degrees, like this one here. So this is greater than 180 degrees, but this one is not, right? That's less than 180 degrees. So it makes this kind of indentation. So this has all exterior angles, and it has exterior angles less than 180 degrees. So this one, convex, all exterior angles greater than 180 degrees. Non-convex, there are exterior angles less than 180 degrees. Another way to characterize convex is that if I draw any two points and connect them by a line, that's a horrible line, take any 2 points, connect by a line, that entire line is inside the region. However, it's possible in a non-convex region to draw 2 points and have a line that is not connected, not within the region. Okay, so I can say that the convex contains all lines, or I could say line segments whose endpoints are in the set. And then non-convex means it does not contain all lines. Line segments, I should say, line segments whose endpoints are in the set. Now it contains some of them. I can take these 2 points and it contains the line there, it contains the line here, but it certainly does not contain all. So you can see that I really didn't need multiple indentations to make this non-convex. As long as there's one indentation here, as long as there's one exterior angle that's less than 180 degrees, you will have a non-convex set. Okay, so getting back to this Theorem 1, I've talked about what a convex polygon is, and you have an idea what that is. And certainly this polygon here is convex. And what this is saying is that I know that the optimal solution is somewhere in the blue region. It turns out that the optimal solution must be a corner point. Now you know what a corner point is intuitively. Here, 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 here. Now we'll see later on when we have more general convex sets, you can define a corner point in a mathematical way. You can see also that corner point is an intersection of more than one constraint. You see this constraint here, they intersect at this point, and this is a corner of the region. Same here, this is an intersection of two constraints, intersection of two constraints, intersection of two constraints. Now it turns out that the optimal solution, whether maximum or minimum, must be one of the corners of the region. So look at what we've done. We've cut down from an infinite number of possibilities to a finite number because there's only 4 corner points. I would say that's a pretty radical simplification. I hope you'll agree. All right, so that's the power of theorem 1. We only need to look at the corner points to find an optimal solution. Right. One more theorem that gives us confidence that we can find an answer. So here we say let R be the feasible region for a linear programming problem. In this case, R would be that blue region that we've talked about up here. This is R here. And suppose that R is bounded. So what does R is bounded mean? Well, R is bounded basically means that you can contain it inside a circle. You can find some circle of some large radius that contains the region. In this case, I could choose a circle with radius 100 based at the origin, and that would contain the region. All right. So if the region is bounded, then any linear programming problem involving this region will have both a maximum and a minimum. Okay? So any linear programming will have a solution, at least one solution. It doesn't say there might not be more than one, but there's at least one solution. So if R is not bounded, then it's not necessarily true that there is a maximum or minimum for any objective function problem. But if it does exist, it must be at a corner point. So at this point, we're in good shape to solve our furniture problem. We have 4 corner points. We can compute the objective function at those 4 corner points. In fact, we've already computed 3 of them. It's just the 4th one that we haven't computed. When we do 0, 0, and of course you're going to have profit 0. That's not going to be optimum unless you're lazy and you don't want to do anything. In this case, we just look down and see which one has the largest profit, and that's 62.50. All right, let's stop there and we'll go on with the next video to generalize this method.